Okay. All right, everybody, let's get started. So I'm sure the burning question on everybody's head is, have I graded the exam yet? No, I have not. I started to work on it this weekend, but it's just going to take some time. My goal is to get that done somewhere between Friday and Monday, simply because, one, I want to get it off my desk and into your hands as quickly as possible, but two, I have an exam in another course on Friday, so I kind of would like to knock it out before I have two exams on top of the advising season starting up. So as AD, I'm going to get pretty busy over the next couple of weeks. I kind of wanted to knock that out pretty quickly. Let's talk about logistics. So the attendance grades are up to date. I counted everybody present for the exam because I didn't take attendance that day. I don't do that on exam days. Homework 4.1 and 4.2 are graded. 4.3 is being graded. I think that one was probably among us the more difficult assignments we've had this semester. I don't think it's going to get more challenging than that because that was a 3D equilibrium assignment, so there's just a lot on that one assignment. Okay, homework 5.1 is due today. I think what I'm going to do is tell the TA to probably extend that deadline a little bit or be a little gentle on late assignments, because I was checking this morning and I think a lot of people haven't done it yet or maybe forgot, oh yeah, we have a homework due Monday. So I'll try and be a little gentle on the late penalties there, but I'm not going to extend anything past today because we got to get rocking and rolling. We have a homework 5.2, which is assigned today and due Wednesday. And I would argue this is one of the more important homework assignments this semester, or at least as it relates to your third exam and the final. This is and just the concept of statics in general. This is a very important assignment. One final thing I'll point out, and my apologies, I thought I had already done this. I had posted all of the notes to Blackboard, but unfortunately I left them invisible, so I know that during the exam review, everybody's like, can we get these slides? I was like, I thought they were there. So my apologies for that. But what I decided to do is just turn everything on. So everything between now and the end of the semester is now visible on Blackboard. You should see everything from today till December. So I don't know if anybody's checked, but everything should be visible now. So far so good? Okay, so with that, let's get into the land of centroids. This lecture is going to be kind of important, but in a roundabout way, it's also going to kind of be repeated over and over again. In other words, if you understand this lecture, this Centroids 2, then what we do for Centroids 3 and 4 and whatnot, you'll kind of pick up on. There are some skills that I think are just seminal for engineers to be able to do. There are certain things that you kind of have to be able to understand. The mechanical engineer and their Carnot cycles, and the civil engineer and their sieve analyses and what have you. But being able to locate a centroid is just sort of seminal to engineering. It's something that any employer or any practicing engineer is going to expect you to understand. It's definitely going to be on the FE exam, regardless of what discipline that you take. It's just fundamental to what we do in engineering. So this is a really important lecture, and the example that we do today is going to be really critical to that. So to be clear, this is where we left off last time. To locate the center of gravity, what we're doing is we're computing a weighted average of just that, the weight. So in 2 dimensions, we're looking for that magic coordinate, that x comma y, where I can lump the entire region of interest as a single vector. The magnitude of that vector is equal to the total weight of the object in question, and the coordinates are where we place that vector to achieve both force and moment equivalency. Now, looking at it in terms of weights, we can either look at it discretely or continuously, either through an algebraic expression or a calculus expression. And that's what the center of gravity is. The difference between the center of gravity and the centroid is that the center of gravity looks at things in terms of weights, and the centroid looks at things in terms of area, in terms of geometry. Okay? So that's what we're going to be looking at today, is how to locate the centroid. And what we're actually going to focus on is our algebraic expression, not the calculus expression. The reason why is because of this. Okay, more often than not, what we're able to do is take a complex region and split it up into discrete, what I would call classic shapes. In other words, I guarantee you, I probably could not go online and find a formula for the centroid of that shape. But I do know that I can find the formula for the centroid of a rectangle, or the centroid of a triangle, or the centroid of a circle, or what have you, or the areas and so on and so forth. So just to make sure that everybody's kind of on the same page, we had a homework assignment where I wanted you to derive the location of the centroid of a triangle. Okay, and everybody should have gotten that done by now. Now what we're going to be able to do is use those formulas to compute the centroid of more complex shapes. In other words, the idea is to take a shape and break it up into simple components. The good news is that there's actually probably more than one way to split this up into simple shapes, but in the end, done correctly, everybody will get the same location of the centroid. The problem we're going to do today, I think it's pretty obvious how you would break it up. But you'll see how it doesn't really matter as you start going through some of these problems. You'll get the same answer across the board. Now, one of the things that is going to be required in order to compute the centroid of composite shapes, if you're referencing classic shapes, is just that, a centroid reference. Okay? This is a snapshot of what's in the appendix of your textbook. I'm going to go ahead and tell you this list isn't complete. There is a much more comprehensive list in your textbook. You can also probably find these online. I mean, if you just started Googling centroid of a semicircle, you will probably find the area. You'll find that the X bar or the Y bar is 4R over 3 pi, and what have you. These are not things that I'm expecting you as engineers to memorize. Okay? Now, I'll level with you, there are a few of them that would be a good idea to have stuck in the back of your head. So, for instance, if you have a right triangle, the centroid is located 1/3 of the leg dimensions from the right angle. If you can sort of remember that, it's going to give you a little bit of an edge. But some of these, I'll just be blunt with you, I don't remember. I don't remember what the coordinate is of the centroid of a semi-parabolic area or a parabolic area. I don't remember that. But I don't need to. Okay, I'm an engineer. I could derive these if I need it, or I could look them up if I need it. Okay, I do think you ought to take some time and look at these. One of the things that's worth mentioning, if you are planning to take the FE exam, which hopefully everybody in this room is, the FE reference manual has centroids that are listed in the manual, very similar to this. The schematics and the formulas may be a little different, so it's worth a look before you take the exam, but they are present inside the reference manual. Now, a couple of items to watch out for. So first off, when you're computing the location of a centroid, you got to take care to ensure. So let's take this area right here. Okay. So if I was computing the location of the centroid, what I would probably do is I would split this into 3 regions. I would have a rectangle that probably looks something like this. I would have a semicircle that looks something like this. And then I would have a circular hole. Okay. Now, when you're computing the centroid, what you need to do is, first off, you need to recognize that holes are going to be taken as negative areas. So if I wanted to compute the entire area, I take the area of this rectangle plus the area of this semicircle minus the area of this hole. I know that seems obvious, but when you're in the thick of it, it's easy to just sort of forget that. So make sure that you're taking the area of the holes as negative. And the other thing is to respect the coordinate system. So what I mean by that is when you start computing the location of the centroid, you're going to define a coordinate system with about which to define that centroid. So in other words, if I say that the centroid is x bar equals 2.7 inches, what do I mean? Well, it's 2.7 inches from here, from your coordinate system. And so you need to respect that coordinate system when you're going through the computation of the location of the centroid. So in other words, if I'm computing my centroids, I say, okay, here's my coordinate system. So for each one of these shapes, I'm going to have a distance. So if we're talking about this rectangle, the center of that rectangle is half that distance, right? And from the coordinate system here, that's positive. For this circle, that's the centroid of that circle, and from here, that's positive. But if we're talking about this semicircle, the centroid's right here, and if I'm expressing that, that's negative because it's going in the opposite direction of the positive x-axis. So make sure that when you're computing the location of the centroid, you respect what sign you're assigning to the areas and what sign you're assigning to your centroid moment arms. Does that make sense? it'll make a little bit more sense when we start getting into the thick of what we're about to do. The other thing I'll mention is that if a shape exhibits some degree of symmetry, the centroid will lie on that axis of symmetry. So for example, if we're looking at this shape here down below, this is sort of a trapezoid. The centroid of the whole region might be somewhere about right there, but it will be along that line that splits the shape in the middle. Okay, so if I was trying to find the location of the centroid for this shape, I wouldn't bother trying to figure it out where it is this way. I know it's going to fall along this line. I just need to find how far up it goes. The other thing I guess I'll mention is that the centroid does not actually have to lie on the shape. Okay? It doesn't have to be on it. A good example might be to think of a donut. If I had a donut, the centroid is going to be in the hole of the donut. It's not going to be on the shape. Okay? So that is very possible. So don't think that if you're computing the location of a centroid and it doesn't fall on the shape, that you did something wrong. You didn't. It probably just didn't fall on the shape. Does that make sense? Okay. All right. So here's the example that we're going to do today. I have a somewhat complex shape, and I want to determine the location of the centroid with respect to the x and y axes shown. Okay. And so this is a somewhat complex shape, but hopefully you can kind of see that we can split this up into a series of what I would call simple shapes. Okay. And what we'll find is that once you start getting into this process, I mean, like I said, this is one of the more important things I think that engineers need to be able to do. That doesn't mean it's difficult. This is actually a pretty simple problem. It's just rote. It requires a little bit of process. Also, if you're fans of Microsoft Excel, Excel can make your life a little easier during the computation. All right. So here's the problem. Let me go ahead and pull this up. Give everybody a sec to sort of copy this down. I'm actually, for the first time and probably the last time in this class, going to cheat a little bit and use this little whiteboard that's sitting right here. I will reference this on the screen, and in fact, a lot of what I'm writing here on the whiteboard is also on the notebook, but this is sort of to prevent me from having to scroll a bunch. A triangle. And we'll say semicircle. Okay. Another thing I will do is, hold on. I will use the technology here. There we go. So that the folks on the video can see that too. Okay. All right. So what we're going to do is we're going to determine the location of the centroid of this shape shown. Now, the way I'm going to handle this is I'm going to split this up into a series of simple shapes. Now, in order to do this, I want to do this in such a fashion that we're all doing it the same way. Okay? So here's how I'm going to do it. And I want to be clear, there's no magic way of splitting it up or ordering it. This is just sort of the way that I've decided such that we all get the same answer, okay? Or at least, not that we're getting the same answer. That's the wrong way of saying it. So that we're all doing it in the same order, okay? So we'll say splitting up. Into simple shapes, okay? And, sorry. Okay. So what I'm going to do is I'm going to draw, so here's my region. Okay. Then I'm going to draw another region over here, another coordinate system over here, and you'll see why. Let's sort of Do that as a dotted line. Okay. So what I'm going to do is I'm going to deal with this shape. I'm going to look at 4 different shapes. Okay. So I'm going to have a solid rectangle, a solid semicircle, a solid triangle. Okay. So I'm going to number these shapes. I'm going to call them 1, 2, and 3. But then I'm also going to have a hole in the cross section. So I'm going to have a hole right here. And so maybe what we'll do is we'll call that 4. And we'll sort of hatch that in a little bit. In other words, like here's the shape, and then I'm subtracting from that this hole. Okay? Now, I've numbered these in a particular way because I'm sort of dealing with the easiest shapes first, and then I'm dealing with the harder shapes as we go along, and I just deal with the whole last. That, in no way, shape, or form, is the quote-unquote correct way of ordering it. You can do it in whatever order that you want. I'm just starting off with something that's pretty basic. Okay? So what we're going to do is, so I sort of copied the schematic over here because I wanted to be able to reference this as we go through the problem. I don't want to have to keep scrolling up and down, so I copied the image over here. So let's start off with the rectangle. Okay? We'll call this shape 1 rectangle. Okay? Now, to be clear, ultimately what we're trying to do is we're trying to compute that weighted average location of the centroid, which is going to be the sum of XA divided by the sum of A, comma, and then the same thing for the Y bar. Very similar to what we did from an integral standpoint. With integrals, we were integrating x dA and integrating dA. Now we're just summing them up. So instead of an integral formulation, we're just using a summation formulation. If you want, those are sort of our governing equations that we're utilizing. Okay. So let's start off with the area. Okay, so if I'm looking at this rectangle, this should be pretty simple. How do I compute the area of this rectangle? What is the area? 120 times 80, right? Pretty straightforward. So 120 times 80, we'll call that BH. I think I can do that one in my head. Is that a fair statement? So far, so good? Okay, now we got to pay attention. Okay, so what I want is an X bar, or sorry, an X coordinate and a Y coordinate. What I mean by that is, so let's look up here. Okay, so would you agree that barring my horrible art skills, that the center of that rectangle, or the centroid of that rectangle, is about right there? So what are the coordinates of this point? That's the origin. How do I get from the origin, which is right here, over to that point? Along the x-axis, tell me what calculation I need to do.
X divided by 2.
Yeah, I need to take this divided by 2, and then along the y-axis, I need to take that divided by 2. Make sense? So we'll say this is, let's see, this is B over, this is B over 2, this is H over 2, and so that is, what is that, 120 millimeters over 2, which is 60 millimeters, and this is 80 millimeters over 2, which is 40 millimeters. Is that a fair statement? Okay. This part right here, this is really the hardest part of the whole problem, making sure that you can characterize the area and the XY coordinates for each of these shapes with respect to your origin. And that's probably the most important part, is that you need to respect the origin, okay? And I'll show you what I mean by that by looking at our semicircle, okay? So the next shape that we're going to look at is this semicircle, okay? So this shape 2, all right? So let's scroll down here a little bit, and I'm going to get this out of the way because I'm going to be looking at that here in a bit. But let's look at shape 2. Let's look at this this semicircle. Okay, so let's look at this semicircle. All right. So what we're talking about is we're talking about that region right there. Okay? Because remember, what we're going to do is we have this solid rectangle, this solid semicircle, solid triangle, and then we're going to remove the hole from it. Okay? So for now, let's just treat it all as one solid shape. So first off, help me out. How do we find the area? Oh, I did it again. How do we find the area of that semicircle? Well, how do you find the area of a circle? Pi r squared. So what's the radius of that circle? 60. All right, that's another thing. Make sure you're reading the schematics appropriately, right? So this semicircle has a radius of 60, okay? But if the area of a circle is pi r squared, the area of a semicircle is pi r squared divided by 2. All right, so pi r squared over 2. Who's got a Casio FX 115 ES Plus or similar scientific calculator with them? Yes, I'm going to make you do some calculations this morning. It's not that cold outside. We'll say 2 decimal places to make sure everybody's on the same page. Anybody got an answer? Come on.
5,654.
There we go. 56, 54, we'll say 0.87 millimeters squared. Do I have a second on that? All right. Just get ready because I'm going to ask for a few of those here in a little bit. So, and she's good for the day. It means somebody else is going to answer the next one. All right. So, let's talk about X2 and Y2. All right. Now, okay. Let's again make sure we understand what these are. Okay. These are the distances from our origin, our defined coordinate system, to the center of each one of these shapes. Now, if I was looking at this semicircle, I would say, you know what? We're probably looking at about somewhere about like that. That's about where the centroid is. Now, let's make sure we're clear on something. This is X2. Now, do you need some fancy guide to look up and tell me what X2 is? Or do you think you can look at this schematic and tell me what X2 is? You're shaking your head yes. What is X2? The 1/2 of 120. It's just the radius, right? In this case. So it's R, which R is 60 millimeters. Okay. Okay, good stuff. Now, Y is a little different. Okay? So let's look at this. Okay? This is a semicircle. This is one of those things I don't expect you to just sort of remember, okay? And this might be the very first day that you've ever seen this formula before. I'm curious about that. We'll see that here in a sec. But let's go down to our centroid reference, okay? So this is our centroid reference. I only copied the sections that mattered, okay? And so we're looking at a semicircular area. So we're looking at this distance right here. And so what these guides will give you is the centroid with respect to a given point. Now notice how it's not telling you where the centroid is left and right because you know it's along the line of symmetry, but it is telling you what this distance is. This distance right here. And it is saying that that distance is 4r over 3 pi. So if I have a semicircle, okay, and I want to find the centroid, I know that that distance right here is 4r over 3 pi, okay? Okay, with me so far? Now, where did they come up with that? You should know the answer to that question because that's what we did on homework 5.1, right? On homework 5.1, you were deriving the centroid for this. It's just the same process, just a different shape, okay? So far, so good? Now, does that mean that we do this? Is that right? No, it is not, okay? Why is that? Back to your schematic. This dimension right here is 4r over 3 pi. That's what this dimension is. That's not what I'm asking for. I'm asking for how far is it from the origin to that point. So if I just put 4 over r over 3 pi, that's wrong. What am I missing? Say it again? I'm missing another 80 millimeters. That's the issue, okay? By and far, one of the biggest mistakes that gets made in centroid land is to just look up the formula and just use it and not recognize that you need to express those distances with respect to your chosen coordinate system. That's what I meant when I said respect your coordinate system. Make sense? All right, so now let's do this calculation, okay? So 4r over 3 pi, so 4 3 pi. And now what do we got? $105.47. Do I have a second on that? Okay. Does that make sense? How you have to respect your coordinate system? Because really, ultimately, what we're doing is, in a roundabout way, we are summing moments. We are summing moments of area. And when you sum moments, you need to sum moments about a specific point of interest. That's our point of interest. So if we're summing moments about the x-axis, how far is it from the x-axis to that area? It's not 4r over 3 pi, it's 4 over 3 pi plus that. That make sense? Okay. All right. Now let's look at our triangle. Okay. So we're looking at this shaded region right here. All right. So the shaded region here. Okay. So how do we compute the area? Let me scroll up just a tad so you can see that one dimension. What is the area of this triangle? 60 times 120 divided by 2. There you go. $120 over 2 is 60. 60 squared is 3,600. I knew that one in my head. Okay? Now, let's do our X and Y. I'll put them right here. Okay, now, let's see if you all remember, without scrolling, what was our answer from the homework assignment? If this dimension here is B, what is this dimension? How did the homework go? Was it tough? There we go. B over 3. And if this dimension is H, this dimension is H over 3. Okay? That one's one I would kind of like remember. Okay? That's going to show up a lot in engineering land. So being able to locate the centroid of a triangle, I'm not saying you need to memorize centroid references. That one I'd kind of memorize, though. That one just shows up a lot. Okay. So what that means is that the centroid is about right there. Okay? So along the x-axis, how do I compute that? I take 120 millimeters over 3, and I get 40 millimeters. Right? But what about Y3? I take 60 millimeters over 3. Am I missing something? A negative sign. Along the y-axis, to get from here to the centroid, we're going down. Okay? Reminded of a Fall Out Boy song. Okay. That's the reference thing. All right. I'm such a dork. Okay. With me so far? Okay. The only shape left is the hole. Okay. If it's okay, I'm going to kind of squeeze that in right here, so I don't have to keep scrolling up and down. So we'll say 4. So the circular hole, all right, so maybe what we'll do is we'll break that up a little bit, break that up, sort of like that, so we know what regions we're dealing with, and we'll do that. Okay, so I know I can squunch that in. So the area of that circular hole, so we're talking about this circle, okay, so the area of a circle is pi r squared, but what do I got to be careful about with this area? It's a negative area because it's a hole. I'm removing that material. So here, I'll do it down here. What's the radius of that hole? 40. Okay, and what do we get for that? So I know everybody has their Casio FX115 ES Plus or similar scientific calculator. There we go. 5026.55 negative 55. Wait, I have a typo there. It's 5026. Right? Okay. Now what about X4 and Y4? Okay. How far is it from the origin along the x-axis to the center of that hole? What's that distance? 60. Okay. What about up? How far is it? 80. There we go. 60 millimeters. 80 millimeters. Now, before we continue, I'm going to take a sec. I want everybody to catch up on this. I want this to have made sense. I don't want this to be complicated. This is the hardest part. If you understand this, the rest is cake. Okay? Trust me. All right. Any questions so far? Okay. So remember, this is our governing setup that we're using. Okay. So we have the area of each shape. We have the x coordinate of each shape. We have the y coordinate of each shape. The only thing left to do is this. Okay. Now, just about every engineer worth their salt that does this problem for a shape like this will do it with a table. Okay, so I'm going to draw myself a somewhat big table. Okay, so I'm going to list each of my shapes. Okay, first thing I'm going to list are the areas. And instead of writing the units over and over again, I'm just going to write them like this. Okay, so what do we have? We have the area, 9,600. The semicircle, we got 56, 54, 87. The triangle, 3,600. But then the circular hole, don't forget we got a negative. $50.26.55. Okay? Now, down below, I'm going to put here a summation. So if I sum these four values, what do I get? Again, making you break out that Casio FX 115 ES Plus. Have a second on that? Okay. Now what I'm going to do is I'm going to list the x values. I'm going to list the y values later. Let's just do it one at a time. Let's do the x values first. So for the rectangle, it was 60. For the semicircle, this was 60. For the triangle, this was 40. And for the circular hole, this was 60. Okay? All right. Now what I'm going to do is I'm going to compute this. Okay. Remember that our formula is the sum of x times a divided by the sum of a. So what that means is that for each one of these, I need to take the area times its moment arm. Area times its moment arm. That's exactly what you're doing when you're integrating, right? You're integrating x dA. So each one of those little rectangles times the moment arm, and you're integrating, you're summing it up. So that's exactly what we're doing. So we need 9,600 times 60. What is 9,600 times 60? It's going to be a big number. We're dealing in millimeters. So when you're dealing in millimeters, the numbers get kind of big. Okay. Now what about this one? Now this one I'll help you with. So I get 339,292. We'll just keep it to whole numbers since this is millimeters that the numbers are so big. All right, 3,600 times 40. 3,600 times 40, I'm getting 144,000. Oh. And then this one's, now hold on, watch this. This is negative times this, so this value is going to be negative, okay? This is a negative area, and I'm getting, let's say, 301,593. So this I'm going to sum up. All right? Now, if you trust me, I'm getting this. 757, 699. Okay? So I propose then that therefore X bar is the sum of XA divided by the sum of A, which is 757, 699 millimeters to the third divided by that. And what do you get when you chug that out? Not letting you completely off the hook. Letting her off the hook. She's already done one. I know she's good. So somebody else. No, I've got some answers over here. So it's not that huge. We'll say 2 decimal places. Yeah. 54.79 millimeters. So I have a second on that. Good deal. All right, so let's do the Y bar one, and then let's take stock of our answer and see if our answer made sense. So Y, so what do we get for Y? And am I writing big enough everybody can read my handwriting? Just I always like to check on that. Okay. All right, so for the rectangle, I think this was 40. For the semicircle, it was like 105.46 or 47. I don't remember which one was it. 46. Oh, okay, okay. This one was negative. This one was positive. Okay, but we got to be careful because remember our areas as well. So this is going to be positive, positive, negative, negative. Okay. So I'll help you out with these. So this is YA. So this one, so just to make sure we're all clear on what we're doing, we're taking area times that. We're taking area times that. Area times that. That, you know, we're multiplying those terms. So this first one I can do. So 96 times 4, 9 is 36, 24, so 384. This one's just messy. This one's straightforward. 3,600 times 20, so 36 times 2, 72, another 0, negative 72,000. And this one's also negative. And so we're doing, you know, that times that. So we're getting 402,124. So maybe I can do a little bit better with my line here. And I'll do a little bit better with this line. All right. So when I sum this up, I end up getting 506,265. So now I can do a Y bar computation. Again, let me scroll down a little bit so I don't have to squunch down when I write. Sum of Y times A so now we have 506. And when you check that out, I'll go ahead and give you that one. You get 3661. So that's the location of our centroid, okay? So So those coordinates are, so, and then I want to go back to the schematic and see if this answer makes sense. But I want to go back to this schematic real quick. Give me 1 second. Sorry. Drag that down. So here's the problem, okay? And what this is saying, so let me see if I can locate this. So, all right, 54, maybe like right there, and 36, so 40, so this is 80, 40's right there, so right there. So it's saying the centroid is about right there, okay? So in other words, if I were to go out and buy a MakerBot and print this thing out, or cut this thing out of steel, get myself a thumbtack, and stick this shape right there on that shape, that's where it would perfectly balance, is right there, okay? So I can idealize the weight of that shape or that area as a single vector right there, okay? Let me stop for a second, see if this makes sense. Most important thing, I would say, the most common mistake I've seen, I'm saying this right now to everybody in this class, I guarantee you somebody will probably still make this mistake on the third exam. When this says 4r over 3 pi, it doesn't mean that you plug in 4r over 3 pi in the table. It's referenced from the datum, from your specified coordinate system. So make sure that whatever x and y values that you use, that they're referenced from a common origin, not just plugging and chugging what the table said. Because if you do, it'll be wrong. Like the answer will be wrong. Does that make sense? All right, I'm going to pull up the QR code one more time. You got to. This is what I'm going to do for homework 5-1. I'm going to extend the deadline to noon today, but no later. So I'll go on to Blackboard and make it noon. With that, that's all I got. I'll see you all on Wednesday.